So now I can describe to you the lock algorithm. Basically, the lock algorithm takes two arguments. One is this name, the dummy node that is associated with this particular lock, and it is also taken my queue node, the one that I'm providing to say that this is my queue node, please enqueue me into this lock request queue. And when I make this call, it could be that I'm in this happy state, in which case I don't have any lock request as ahead of me. But if it turns out that when I come in, there is somebody else using the lock, then I'm going to join this queue. And it has to be done atomically. And there are two things going on here in joining this queue atomically. What I do is I set the last pointer. This list is always pointing to the last requester. So it used to point to this guy. He was the only requester. I came along, so we have to fix up this list so that this pointer is going to point to me as the last requester. And I also have to fix up the current requester to point to me. And once I've done that, then I can await the predecessor, namely this guy, to signal me by spinning on the guarded variable that is associated with my data structure. And the other thing that I would do as part of joining this queue is to set my next pointer to nil, because there's nobody after me. I just made the lock call. Notice that when I'm joining this queue, I'm doing two things simultaneously. One is I'm taking the pointer that was pointing to him and making it point to me. And I also need the coordinates of the previous guy so that I can set his next pointer to point to me. So I have to do this double act. So this has to be done atomically as well. So joining the queue essentially is this double act of breaking a link that used to exist here, make it point to me, and get the coordinates of this guy so that I can fix him up. And remember that this is happening simultaneously, perhaps, with other guys trying to do the same thing, joining this queue. And therefore, this operation of breaking the queue and getting the coordinate of my predecessor has to be done atomically. And in order to facilitate that, we will propose having a primitive operation called fetch and store, an atomic operation. And the semantics of this fetch and store operation is that when you make this call and give it two arguments, L and me, what this fetch and store is going to do is it's going to return to me what used to be contained in L. So what used to be contained in L is my predecessor. So I'll get that, and I'll get the coordinates of this guy. And at the same time, it's also storing into L a new node that is the pointer to the new node that is me. And so that's what is being accomplished by this. The double act that I mentioned of getting my predecessor's coordinates and setting this guy to point to me is accomplished using this fetch and store operation. It's an atomic operation. And clearly, if the architecture is not having this fetch and store instruction, you have to simulate that with a test and set instruction.